This is the video report for the Sallen Key assignment. So first off, I'm going to draw a Sallen Key circuit. So we've got our two resistors. I'm going to label R1 and R2. Down here we have capacitor, as well as capacitor up here. So this here is C2, and this is C1. And in here we have an op-amp as well, positive and negative. Okay, so just wire this all up like that. And I'm going to ground this here as well. So now this here, VBN of T. And from this point here will be V out of T. Like that. So now that we have the circuit drawn, I'm going to draw out the transfer function. First things first, we're going to say the cutoff frequency in angular frequency is 1 over the square root R1 C1 R2 C2, and the transfer function h of s will be equal to omega 0 squared over s squared plus 2 zeta omega 0 s plus omega 0 squared. Okay, so now also zeta is the damping ratio, and it is equal to it's equal to R1 C2 plus R2 C2 over 2 root R1 C1 R2 C2. So here we've got zeta and we got our omegas. Now so S is equal to sigma plus j omega. But when sigma is 0, so when sigma is gone, then in which case S equals j omega, this is our frequency response. So we can write that in. H of omega equals omega, just not 0, C, omega C squared over, say, omega C squared, move that over to there, minus omega squared, because J squared is minus 1, plus J 2 zeta omega C omega. So this is our frequency response. Now to convert from frequency response or S-plane response, the transfer function, we can use inverse Laplace, which is very simple. So basically, all that we care about is that S by, say, V out of S is equal to dV out T dt. And this is S squared. This would be the second derivative, and the third derivative for the S cubed. So we can use this to convert from the transfer function to the differential equation. So first we'll say h of s equals v out of s over v in of s, which is equal to this omega c squared over s squared plus 2 zeta omega c s plus omega c squared. We're going to cross multiply, so then v out of s by s squared plus 2 zeta omega cs plus omega c squared equals v in of s by omega c squared. Now, in the end, we'll want v out to just be v out. So the only time where v out is multiplied by an s is here. So we want to make that equal to 1. So if we divide both sides by omega c squared, then we'll have it equal to 1. So we'll do v out of s by s squared over omega c squared plus 2 zeta over omega cs plus 1 equals v in of s. Then we want v out to be by itself, so we'll do v out of s by the 1, and then we'll have the other v out of s by s squared over omega c squared go over here, and so for 2 zeta over omega cs. So then that equals v in of s minus v out of s by 2 zeta over omega cs minus v out of s by s squared over omega c squared. And then if we use this rule earlier, we can change these to be in terms of time. So v out of t equals v in of t minus 2 zeta over omega c dv out of t dt minus 1 over omega c squared d squared v out of t dt squared. Okay, so now what we want to do is work out the natural frequency and the damping ratio. So we have our values. R1 is equal to 18 kilo ohms. R2 is equal to 3.9 kilo ohms. C1 is equal to 100 nanofarads. And C2 is equal to 3.3 nanofarads. So we'll get R1, C1, R2, C2 is going to be equal to 2.32 by 10 to the minus 8. So then we know that omega c is equal to 1 over square root 2.32 by 10 to the minus 8. So omega c is equal to 6,570 radians per second. The cutoff frequency in terms of hertz is 1 over 2 pi root R1 C1 R2 C2. So then that's going to be equal to 45.67 hertz. And zeta, pretend it looks like zeta, is equal to R1 C2 plus R2 C2 over 2 root R1 C1 R2 C2. So if we find out these values, then we have 59.4 by 10 to the minus 6 plus 12.87 by 10 to the minus 6 over 2 root 2.32 by 10 to the minus 8. So then zeta is going to be equal to 0.237. Okay, so to start our simulation of the Sallen Key LTspice, we will add in our resistors. So we've got R1 and R2, and also our capacitors. We've got C1 and C2. We also need an op-amp, so add in the op-amp here, and then also include its lib file. Just like that. Now if we get a signal generator and put it right there, we can just connect all the wires between the components. Once I'm done this, I'll be able to edit the component values. We've got 18 kilo ohm resistor, 3.9 kilo ohm resistor, 100 nanofarads, 3.3 nanofarads, and this needs to be a pulse. So we want it to be 0.1 so it doesn't cut when we save it. Delay of 4 milliseconds, rise time of 1 pico, fall time of 1 pico, on for 8 milliseconds, period 16 milliseconds, and lastly just a 1 cycle. So now if we add in our transient analysis for 12 milliseconds and run that, we can see our step here at 4 milliseconds, and then at node 2 we've got our step response. So to save this, we just add a dot while. copy the file name, and we're going to call this vout.lab. So it's going to be 16-bit resolution, 160,000 hertz sample frequency, and it is at node 2. So if we just pop that there, we should see our output file. So this has now fully simulated the Sallen key and output the file to the vout.lab, which we will later input into MATLAB. Now that we have our step response from LTspice, what we're going to do is upload that to MATLAB. So srfs. We're going to be using the audio read function. Audio read, and then it's called vout.wav, like that. And then we're adding the time domain as well. So it's going to be for the length of step response -1, and then we'll just divide that by the sampling frequency. Yeah. So if we plot them, we should get our step response. There we are. Yeah, looks good. So now if we add some labels, so X label, we're going to say time, which is going to be in seconds, and then Y label will be the amplitude. Just like that. So now if we open up this, we've got our labels. Excellent. Okay, so we can also get the impulse response now if we take the derivative of the step response. And then we're going to get the absolute value of the FFT of the impulse response. And then we can plot that. Before we plot that, we want to add the frequency domain. So we'll say frequency axis equals 0 to the length of x -1 divided by the length of x by the sampling frequency. Then if we plot the frequency axis versus x, we should see, yes, we've got our frequency response. Now, what we want to do is we're going to add an x lim to that. So that is just the first half. Like that. We're going to add the next label, which will be called frequency. That's going to be in hertz. And then the Y label. Then the Y label will be the magnitude. Magnitude. Do that again. Yeah, looking good. So the last thing we can do is if we get the semi-log along the x-axis, and then we're going to do the frequency axis versus 20 by log 10 of x. We can see that there, so we'll just quickly add in some labels as well. Like that. And now we can look, so we got it here. Now this is at -20. The reason for that is because in LTspice, we set the step response to be a 0.1 volt instead of 1 volt. So if we were to multiply, SOR by 10, let me just quickly do that. SOR equals SOR by 10. Then I want to do IOR, and then X, and it's actually the same, and then this. Now if we look here, yeah, now we're starting at 0. There is another way to get the step response, and that's using MATLAB. So if we use B&A coefficients, we can get from the transfer function. We can do it in MATLAB. So here in the Akawa calculator, we can just copy these values. There's our B, then our A is going to be like this. So if we just copy them, that'll be 1. and then that there, just like that. So now we want to make, so it says this one's equal to the transfer function of BA, just like that. Yep. Actually, I'm just going to show you that it is the same as the other one. So we got 4 by 10 to the 7, about 3,100. So that, yep, that's basically the same, and then that's basically the same. So that shows that this is the same as our circuit. So now if we say step of sys1, it will show us the step response of our transfer function once it loads in. And we'll also be able to do this for the Bode plot as well, which I'll do just after this loads. Shouldn't be too much longer. Maybe it will be. There we are. Oh, there we are. So here's our step response, which looks the same as before. Yep, everything looks correct. So now if we do Bode of sys1, that will give us the Bode plot for the signal. And then we'll also be able to get the frequency response for the signal with a function called freqs, freqs. Here's the Bode plot. So you can see it's the same as before, 0, and then it goes up just about here. And then, so yeah. And then if we do h and omega equals freaks, b and a, and then plot omega versus the absolute value of h, that should give us the frequency response. Which here we are. And yeah, that's about what we're expecting. The last thing we'll be doing with MATLAB is simulating what the Sallen Key filter would do to an arbitrary signal. So I'm going to use is signal 1 from the speech filtering assignment. I'm going to show you what this looks like now. First, you got to read it in. So we input fs equals audio read. Let's go signal for 1.5. Like that. Then we also want to make the frequency for the bottom. So we've got 0 and then length of the input -1 over the length of the input by fs. And we'll do x equals the absolute value of the FFT of the input. Now we can just plot f1 versus x. And then just xlim that from 0 to fs over 2. And then here we are. So you can see this is all the noise that we want to get rid of. And this here is about the color frequency, so it should stay the same for here. Be a slight increase around here, and then everything after that basically should be removed. So what we do, so first of all, I want to open up this. This is from earlier, so we can just run this to get the values again, which is done. So now what we're going to do is use the linear sim function. So we just do system1, then the input. Actually, sorry, before we do that, we need to do the time, which is from 0 to the length of IP -1 over fs. And then we just need to do linear sim, this one, input and time. And then this will simulate. So here we've got the gray was the original signal, very noisy. And you can see here the blue, we've got the new signal, which is looks much more like actual speech. To build a circuit, we start off with our quad op amp, the TL084CN. So we're going to first we need to power it. So I'm going to add this blue cable and this red cable, sorry, orange cable, which will be positive 15 and then negative 15 volts. We also want to add a grounding cable so we can connect our conger clips to the circuit. So we'll start off with our 18 kilo ohm resistor right there and our 3.9 kilo ohm resistor. Just go right beside it, just like that. So we want to connect the output of this second resistor to the positive input of the op amp. We also want this capacitor here, which is going to be C2, so it'll be grounded. So we'll also add in a grounding cable like that. And then we want to add in C1, which will go from this point here to the output. So this here is the connection between the two resistors, so that's going from there to the output. And we also lastly want to short the negative input and the output like that. Okay. So now if we stick this green wire here, we have the output for our Sallen key, with the input line being right here. It's functioning Sallen key. The only issue is I was getting when we were running step response, there was a slight jump at the start of the step, and then it would flatten out. So to fix that, I simply added a buffer amp. So only for that is to short the output and the negative input, like earlier. No, just like that. And then we just connect the output of that to the input of the Sallen key, along with this white wire just to hold down that longer ground cable. And then we have an input wire here, so that you can input your signal here. You power the op amp with positive and negative 15 volts. You've got it grounded here, and then the output will be here. The last step in this is connecting up the circuit to the power supplies. So this is for the op amp. So we've got a black wire here connecting the negative terminal with the positive terminal. So this means that the positive terminal here is at 0 volts. So obviously this orange cable here is going to go to the positive input for the op amp, which is labeled orange cable on the circuit. And this green cable here is also at 0 volts coming from here. So that's going to go to ground on the circuit board. But then this blue cable here that I've labeled, this is 15 volts. Well, in this case, it's not, but on the actual circuit, it was 15 volts here. But this is 0. That means this must be minus 15 volts. So then that's where we got our minus 15 along this blue cable, which connects to the negative input for the op amp, for the negative power for the op amp. This here is connecting up the circuit. So here, this red wire is connected to orange. That was the that's the positive 15 volts. This is the negative 15 volts connected to blue. These are all the ground cables connected up to that ground wire. And this here, so this here is the input signal coming from the signal generator. This probe here is picking up the input signal, which will display it on the oscilloscope, and this probe here is picking up the output signal. So here we have our first sample point, which is at 517 hertz. So you can see that they're similar enough, but if we go to this graph here, we can see at 517 volts, the voltage of the output should be 0.53, and it's 0.51, so it's pretty close. This graph is just, it's got the resistor and capacitor values, it's got the cutoff frequency, zeta, and then the transfer function. So the blue one here is the magnitude of the transfer function, but it's multiplied by 0.425 because that's the magnitude of the input signal. So then the output signal here, and this is the phase. So we can see that they're pretty close. Here's the next one's at 825 hertz. It's about 740 millivolts. And if we go here, let's put 700, sorry, we put 825 in here. We get it's about 800. So it's not quite the same. It's a bit lower here. Sorry, it's a bit higher in theory than it is in practice. So if we go back to here, to the next one, this was the highest we could get in practice, about almost 800 millivolts at 944 hertz. And if we set that to 944, sorry, 944, we can get it's about 0.91. So it's about 100 millivolts off theory. If we look here, the highest point in theory is at 984 hertz, but at that point on the oscilloscope, it was actually it was decreasing. This is down to inaccuracies in the imprecisions in the resistors and capacitors, and of course the op-amp would add its own imprecisions as well. So here we've got 1,420 kilohertz, sorry, 1.42 kilohertz, which is giving us 392 millivolts. So it's starting to decrement here. We set 1.42 here, so 1420. We say it's about 0.4, so it's actually close enough again to what this was. And you can see the phase shift is starting to happen. Now, it's hard to see, but you can see there is a slight difference in the peaks here. The peak of the output is here, and the peak of the input is there. And then here we have at 1,929 hertz, we've got 172 millivolts. So if we set this to 1,929 hertz, we get this 0.16. So it's, once again, not far off, but it's not exactly the same. And you can see the phase shift is pretty much fully gone to, they go inverting, which once again you can't really see because it's not a great quality photo, but it was in fact pretty much just inverting the input signal. Here we have the first step results we took. So you can see what I mentioned earlier in the circuit building, that the step had this bit of a jump to it, which isn't really ideal. So what we did was we added that brown cable connecting to the buffer amp, and then that gave us this much smoother step. And you can see here, the step looks very similar, almost identical to what we had in MATLAB and on LTspice. And it stops after about 4 milliseconds, which is the same as what we were getting on LTspice and MATLAB.